Hello, everyone. I'm Laksh, Senior Software Engineer at Recursion. Today, I'm going to be talking about how we migrated our JSON DB to relational DB using Apache Beam. Well, thanks for joining my talk. A little bit of overview about Recursion before we dive in. We're a tech bio company. What we're doing is like leveraging ML AI techniques to optimize the drug discovery pipeline. We have generated petabytes of data. As I mentioned, we're an ML-based company. We thrive on data. So our robots run millions of experiments every week to generate these data. For example, millions and millions of images that our vision models use. We have offices in North America and Europe. I'm based out of Toronto. Yeah, what we mean by industrializing drug discovery is like, we call it the T. On the left side of the T, you can see like the traditional biopharma pipeline. It takes $1 billion and almost a decade to discover a drug for a disease. On the right side, what we're trying to do is like industrialize and embed what we call recursion OS and like different stages in clinical pipeline or discovery pipeline to optimize this, like, and fail faster and get to drugs faster so that patients who are waiting for cures for diseases can benefit. How we use Beam, our Dataflow recursion in general, we have a few use cases at Recursion. We do a lot of image processing. Our microscopes generate a lot of images every week. For example, one such processing is like converting them from like one format to another. And we also use Beam for like dataset packaging and publishing. Last year, we released a dataset called RxRx3. It's 100 terabytes of images, basically images of cells, one of the largest datasets, the largest dataset for phenomic modeling, I guess. And yeah, we use Beam to like package these things, basically group these different sets of images and bundle them, apply transformations, and then like upload to like some sort of GCS or S3 so that people could download from there. And another use case that we use Beam is processing our ML artifacts. So we have a lot of machine learning models, and as a side effect, in some of these pipeline processes, we generate embeddings. And naturally, we would do some sort of aggregation or statistical transformations for these embeddings, right? But yeah, those are some of the use cases. But how many of you here have done some sort of migration in the past, be it API, database, or like, yeah, it's kind of like the nature of our job, right? Technologies become stale over time, or the decisions that we made to like use one technology or the other become stale. Now we have to move to bigger and better things, right? But yeah, like we were faced with a similar scenario. We were doing like some service migration, and part of the migration was to like actually migrate our database too. We'll get in that in a little bit. But yeah, we don't really throw compute at a migration problem. But yeah, this was an experience of like how we did that and like what we learned from it. Yeah, some context for the database migration. We were using something called Cloud Datastore as a database before for one of our applications. And Cloud Datastore is basically like a JSON store, like MongoDB, so to speak, but managed. And yeah, why did we want to move away from it? Because Google decided to deprecate Datastore, and then they moved on to something called Firestore, which is like an upgraded version of Datastore. Naturally, we have to like upgrade to Firestore at some point, but we had backward compatibility, so we're just like stuck with Datastore for a little while. That was also an opportunity for us to like explore other options. Do we really need Datastore? Do we really need like JSON store, right? Turns out we didn't, because after like a few years of using Datastore, we realized that the decisions that we assumed that we needed Datastore for are not valid anymore. One example could be like Datastore indexes all the JSON columns, which is really unnecessary unless your users are querying each of the columns that you have in your database, right? Which is not true, but we had like 10 terabytes of indices in the database, basically paying money for indices that we don't even use, right? That's one example. And the other example is like, we don't really need like an unstructured database because our data is like a semi-structured one. So we could use something like Postgres, which has JSON columns, and it's a boring way of doing tech. Like it has survived like, I don't know, decades right now. It'll scale well as we grow along. Yeah, we were also migrating the service that we're using the database as well. So it was like sub-level of that migration. But yeah, so we came up with a high-level approach of how we want to move this data. For example, like we wanted to export the data into like an offline Postgres instance until a certain timestamp. And then we decided to like write double writes, we call it. Like it's basically writing to Datastore and Postgres at the same time from the application level, so that any new data that gets generated is already in Postgres. We only need to like backfill the old data, right? And then like migrate the delta between the time between the export and like the double writes. right? And then like switch all the services to read from Postgres. That's kind of like the migration plan we had. We totally could have skipped the first step. We could have just started the double writes and then like export the backfill like later. We could have skipped the delta step, but we decided to do it this way because we were able to like parallelize the work, and we started the migration earlier than we started the code changes for the double writes in our application. The migration itself was consisting of like two parts. So part one is like basically like exporting all the like data into like a JSON file using one of the pipelines that Google Dataflow gives as a template. And then the second part of the pipeline, which we wrote, basically like normalizes the JSON and then like dumps it into like Cloud SQL, which is Postgres. So yeah, and part one, that's the first pipeline where we used an off-the-shelf pipeline, which is written in Java that automatically like exports data from Datastore, right? All we needed to do was like just use that template and then like specify some inputs, and it'll just like give a bucket pattern, and then it'll just export the data. That's called like Firestore to Google Cloud Storage. Like I said, like Datastore is deprecated. They only had like a Firestore template, and it was backward compatible to like Datastore. We were able to use it. And I have a link to a code that you can look at later. But yeah, one of the reasons that we wanted to go down this route was like we didn't want to like put live load into our data store like during the migration process. So making an offline copy or like export from the data store like enabled us to like just like work off of the files that were exported rather than putting like load on our live DB, because this application that was using this DB at times could receive I think 2,000 to like 6,000 RPS based on the load. Yeah, and then the Dataflow. There were like a couple of gotchas with the Dataflow template itself. Like when you export the data, you want to supply a query to like how do you want to export, right? Let's say you give like a date range, that's an inequality filter. And if you do that, like it hits the parallelization in some ways that you don't want to. And the template also gives like a user-defined function for you to like add these filters on. But initially we did not know that. So this is a sample of one of these like runs. Forgive me if it was too small, but yeah. It has two inputs, this pipeline. Basically the query, which has an inequality filter right now, but we'll get into it. It's basically a select star from all of the data, right? And then a bucket pattern where to like, oh, where do I like put these files to? And that's all you need to specify. And some of the like auxiliary like params, like how many workers that you can throw out to this Dataflow job. And that's the inequality filter that I was talking about. When we ran this pipeline, you could see this warning from this pipeline. Basically like, hey, I'm not able to parallelize this query because you give an inequality filter. That's like something that we didn't know about, but it was taking like longer. Like if we went down this route, like giving like some date ranges or something like that in the query, it won't parallelize, it'll sequentially do the export. That is really, really expensive in terms of like time. And it'll take days to even do the export, right? So that's the warning. But then they also give like a user-defined function that you could like, that is built into the pipeline that you can write in JavaScript, whatever filter you need. For example, here, like we use like the time filter. Hey, until this time, like filter out all this data. So that's a user-defined function. This way, we don't need to like use like the filter in the query, which allows you to like utilize the maximum parallelization in Dataflow. As you can see, like it was able to like split the query into like, I don't know, some 20,000 splits. I don't know how the sharding works underneath. Somehow they parallelize. But yeah, that's a screenshot of the job. You can see right here, like this is one of the test jobs. Like the query matched about like I think 25 million records, and then the user-defined function like filters out based on your criteria and then like dials it down to like 1 million, whatever you need. But it's really faster than adding the filters in the query in the first place. But yeah, once you do that, like you have all these files in a bucket. I think we had about like 4,000 files each. As you can see, like each is like varying in sizes. You can see like why it would generate like a lot of like files, because if you have like only one file to like output to, like that is a bottleneck for parallelization. But yeah, moving on, which brings us to the second part of the migration, which is like how do we get this like all this JSON file into like the Postgres instance, right? Basically, we need to like make all these JSON, normalize them. So that's a really interesting part in terms of like this pipeline, because it's not a straightforward like migration. This is where the migration problem becomes a data ingestion problem. We had about like 1 billion records that we need to like normalize, and we don't have foreign keys lying around. We need to like establish that. Basically, this is equivalent to like all the writes that have ever happened to Datastore in the last couple of years needs to be replayed to this new database. So it becomes like an embarrassingly parallel data transformation problem, and Dataflow and Beam is like a perfect fit. At least we thought so. But yeah, this is the pipeline like that we wrote, and you can see there are like 3 functions, actually 4, but yeah. it reads all the JSONs in parallel from the buckets. And then like each JSON record goes through that batching function, which we'll get into in a little bit. And then like once you batch those JSONs, then you just like run it to write JSON to Postgres, which I didn't use the SQL Alchemy to like insert into like Postgres, but that's like out of the scope for this demo, I guess. Yeah. And then like whenever there's an error, like we would basically write them as JSONs again so that we could just feed it back to the same pipeline with the bucket pattern as like the error outputs, right? So that's the reusability that we liked. And yeah, you could see like we flatten out the batches using FlatMap. And yeah, the batching function itself, this was kind of like surprising to me that also this was like done like a year ago. I don't know if the information is outdated, but a batching function was not available in Apache Beam. There was a group by function, but you need to like use like group by keys and things like that, which really didn't fit our use case. All we needed was like, hey, we have this list of JSON records. We just need to batch them on a random order. That's it, right? There was not a simple pipeline or like simple function that was part of like Beam.io or something like that to like, we could just import. So this is the only thing that we had to like write. It uses like global windows. So it inherits like the do function. You can see there are like 3 components to this batching function, as every do function has. There's more than that, like there's tear down and things like that, but we didn't need that for this. There's a start bundle where your like input P collection like comes in, and then like process gets called for each of those input. And you can see like we could accumulate these things based on the batch size. And then when the bundle is kind of wrapping up, like we just like insert into downstream functions. And yeah, this is like the actual jobs like snapshot. I only have screenshots for all these jobs because Dataflow doesn't like store job details beyond I think 30 days, at least not in the UI. Maybe there's a way like you can reach out and like get these data, but only screenshots for now. But yeah, you can see like we read from like the JSON, buckets, and then like group them into batches, and then like shove it into Postgres. And you can see the wall time was like I think 680 days. It's about like I think a couple billion records. But I don't know what that wall time means in general. Like, would it have taken like if you use a single worker 600 days to like do the same thing? I don't know. But yeah, some of the job metrics that like these are all a screenshot from the original job. You could see it finished about in like 16 hours with parallelized across like I think 1,000 vCPUs. We only used like a general purpose machine. We didn't like need like a specific vertical scaling like bigger machine or anything like that. And yeah, total vCPU time was like 16,000 CPU hours. Yeah. I think we use batching of like 20,000 batch size for like batching the commits into Postgres. This was like the cost aspect of the entire job. I mean, we did run like the Delta job and everything like after, but those are like very minimal compared to this, like huge, like the first backfill. It's about like $1,200. You can see, I think vCPUs cost the most. Memory wise, not as much relative to vCPU still. But this is like a drop in the bucket in the grand scheme of things, like for like a migration job that your like internal systems use this like database, right? But yeah, hypothetically, what if we did not use Dataflow? Like how we would have migrated this, right? Like we were exploring other approaches too before like started using Beam or Dataflow for this. It would have to be like a batching script, some sort of like a boring way, like where you read from like Datastore and then like maintain the progress of like how many records have gotten into like Postgres. But you need to like take care of the concurrency, like, I don't know, parallelism, et cetera, right? You need to track the progress of the migration. And then you can rent VMs in the cloud. And like this was like a general purpose, like price VM, if you could rent, it's like 3 cents or something like that for like per vCPU per hour. Assuming, let's say you were able to do this batching for like, and the batch job finishes in about like 20 hours, it would have taken at least $700 or like plus memory cost, plus extra data, because you need to take care of all the dev time yourself. But yeah, that's just an example. Probably it would have been cheaper this way, but I would take other approach any day. Some of the takeaways from this was like batch commits were like very, very important. It was so important because like we didn't do the batching first. We just like added a function, like just ran the pipeline initially. It was extremely slow, so slow that assuming, even though we were like able to parallelize to like 1,000 workers, each worker like does like 1 commits per second, like Postgres. And like we were moving along like 3.6 million records like an hour. Theoretically, it would have taken at least like 20 days if we didn't do the batching, and would have been really, really expensive because we were holding on to the VMs for like 20 days, right? But yeah, like glad we did the batching. And then the other takeaway was like we were using Cloud SQL, like our Postgres was on the cloud, so we were able to like upgrade and downgrade like the machine configuration. Like before this whole migration, we just like got a beefy machine, and then like after the migration, we just dialed it down. Yeah, it was very useful for like pre and post migration. And then like this was another takeaway was like the cross-platform powers of Beam, which I really like. As I mentioned earlier, the first pipeline was written in Java from the community, and the second one, like we wrote it ourselves because we were basically like a Python shop. And yeah, error handling and repeatability was like so seamless. All we need to figure out was like how do we like output our errors, and then in a way where you can like get it back to the pipeline. We use the pipeline, right? And yeah, relatively no downtime, because like we had an offline Postgres and we just slammed it with like compute, and then once that was ready, we just like switched our application to like read from it, right? There were like hiccups. I wouldn't say zero downtime, but it's more like relatively minimal, no interruption at all. And yeah, it's definitely not a boarding approach. This is not a conventional way to like do migrations, throwing compute, like. But it worked for us. All we had to do was like write two functions, like batching function and write to Postgres. We could have done like more optimizations in general in Beam, I guess, but it worked for us, and relatively, in the grand scheme of things, it was cheaper to do so. Dataflow did the rest. Yeah, and that's kind of like the talk. And thank you for your time. Thank you for the sponsors and organizers, and thank you for Recursion for letting me be here. Any more questions? Yeah, feel free to reach out to me on LinkedIn.